Thank you. Okay. Okay, perfect. Hi. So I'm Kenzie. Nice to meet you all. And I'm tasked with giving an overview of fast radio bursts, and hopefully try and show you where we are with the questions of what are they and how we can use them as probes of extreme plasmas. So we'll start with what is a fast radio burst. Fast radio bursts are millisecond duration radio transients that one example is shown here. This is the first discovered FRB, and you can see the signal swept from high frequencies to low frequencies. This is due to an effect called dispersion. So as the radio waves propagate through some ionized plasma, they have this frequency-dependent time delay that is proportional to the DM, or the dispersion measure, which is the integrated column density of electrons along the line of sight. So you can think of this like a proxy for distance. So the farther this thing travels, the more electrons it interacts with, the higher the DM, the higher the time delay. And so this type of transient wasn't the surprise when this was discovered, because we see these dispersed radio transients from our own galaxy. We see galactic pulsars produce dispersed millisecond duration transients. But because we have these pulsar observations, we have a relatively good idea of the distribution of electrons in the Milky Way's interstellar medium. And so we know for this event that only a small fraction of this dispersion is coming from the Milky Way's interstellar medium. And that leaves behind a whole host of electrons that are unaccounted for. And the interpretation there is that it's coming from the intergalactic medium and maybe even a host galaxy, implying that this thing is extragalactic. And so what that means is that this transient is very luminous. So here is a comparison of the luminosity on the y-axis as a function of duration on the x-axis compared FRBs with pulsars. You can see they're similar duration transients, but there's over 10 orders of magnitude difference in their luminosities. And so that begs the question, what are FRBs? There's lots of theories out there as to what they could be. Most of them center around some type of compact object, neutron star, or black hole. The most promising model for FRBs are magnetars, or highly magnetized neutron stars. The reason is, well, we know that there's galactic neutron stars that produce millisecond duration radio transients. So what if we take those neutron stars, crank up their magnetic fields several orders of magnitude, then suddenly we have a much larger energy budget from which we can draw these higher luminosity radio bursts from. But more compellingly, back in 2020, a galactic magnetar, SGR 1935, produced an FRB. And so if we'd placed this magnetar at some nearby but still extragalactic distances, we would have detected it and called it an FRB. And so the conclusion there is that we know that some FRBs are coming from extragalactic magnetars. One thing that slightly concerns me is that the luminosity didn't quite hit FRBs. It's close, and it's orders of magnitude higher than other galactic sources, but it's not quite as luminous. And as I'll show on the next slide, there's a number of other observational things that we see in the FRB field that put into question whether magnetars produce all FRBs. So for example, we have classes of FRBs. We have non-repeating and repeating FRBs, where we currently in the field don't know if non-repeaters, we just haven't waited long enough to see a repeat burst and whether they all repeat. What we do know is that there are observational differences in these classes of models beyond the repeatability. So I'm showing here that the one-off events or the non-repeaters are broadband in general in the CHIME band of 400 to 800 megahertz, and the repeater bursts are narrowband in general. And similarly, their timescales differ as well statistically in the populations. The non-repeaters are narrower in time compared to the repeaters, which are broader in time. So there are some observational differences. Whether this is because of distinct progenitors, we don't know, but it's worth noting. We have an FRB, a repeating FRB that is periodically active. So the bursts are emitted within a 5-day window during a 16-day cycle. There's theories to suggest that this could be a slowly spinning magnetar, but based on what we know observationally about magnetars, there's magnetars that are kind of second period, and some of these long period transients get into kind of minute territory, but 16 days is a bit of a stretch. So I think there's other models that, at least to me, seem more compelling, that this 16 days could be explained by a binary system where the 16 days is the orbital period. We have an FRB that's living inside a globular cluster. And so this is an older stellar population. If this is a magnetar, it wasn't created through the core collapse of a massive star, as you would predominantly expect. If it is a magnetar, it was created through a more evolved formation channel, like accretion-induced collapse of a white dwarf. But maybe it's not a magnetar at all. And then there's some examples in the literature of FRBs that are co-located with these compact, persistent radio sources, the origin of which is also a mystery. We don't know what these are. The leading theory is that they could be a magnetar wind nebula. So you have a magnetar that's flaring and producing the radio burst, but it's also throwing a magnetar wind and fueling this radio nebula. However, why only 4 of the entire population so far show these still remains a mystery. And I will refer to Alex's talk in a few talks from now, and she'll talk more about environments of FRBs in general. So yeah, all of this to say, I'm not sure that they're all isolated magnetars, and that's kind of the question that we want to answer. And why do we want to answer that? Well, FRBs are very powerful probes. So I mentioned already dispersion earlier, which is a trace of it's basically a count of the electrons along the line of sight. Nina gave a nice flash talk yesterday on scattering. Scattering tells you the distribution of electrons along that path. And then we also have Faraday rotation, because FRBs in general are very linearly polarized. That tells you something about the magnetic field of that plasma. And so depending on where FRBs come from, what kind of compact object systems, it means that we have these probes of densities and magnetic fields in these environments. And that's quite unique when it comes to transient astronomy. Beyond that, the better that we can understand the local plasma, the more useful FRBs as probes of all of the other plasma along the line of sight, because they basically count all of these electrons and the distribution of electrons and magnetic fields along the entire path to Earth. And so, yeah, if you care about host galaxies, then we can probe the interstellar medium of the galaxies, we can probe the CGM, the IGM, anything intervening the line of sight, and then the same for the Milky Way as well. So to answer the question, what objects produce FRBs, the key is really into studying their host galaxies and their local environments. This is done throughout transient astronomy. For example, in gamma ray bursts, you have the long and short GRBs we've had many talks on already. And long and short GRBs are found in distinct environments. So you have the long GRBs living in low metallicity environments, linking them to the death of massive stars. And then you have short GRBs that are living in more quiescent environments in the outskirts of their galaxies, linking them to compact binary mergers. So we want to play a similar game with FRBs. What do we know so far? Well, fast radio bursts, the non-repeaters, their host galaxies seem to trace star formation. And so this is completely in line with a young neutron star origin, magnetar origin. However, for the repeating FRBs, they're kind of found all over the place. So we have repeaters that are living in star-forming galaxies near star-forming regions. But we also have some more quiescent environments. For example, this FRB that is highly offset from this quiescent elliptical galaxy. And then the globular cluster FRB that I already mentioned a few slides ago. And again, I'll refer to Alex's talk because she'll talk more about the environments. But all in that to say, I don't think that this necessarily tells us that repeaters and non-repeaters are distinct progenitors, because we're not quite comparing apples to apples here. For the non-repeaters, we're really looking at global host galaxy properties, whereas for the repeaters, we are able to do more local environment studies. And this is due to the fact that current telescopes are able to find FRBs and localize them to host galaxy precision. Yeah, get you like the telescope shown here, so ASCAP, DSA 110, MeerKAT, etc. They can get you to kind of like arc second, sub-arc second scale, which will tell you the galaxy, but not really where within. Whereas for the repeaters, we can do follow-up observations with higher resolution, such as the European VLBI network, do very long baseline interferometry, and then you get to milli-arc second scales. But the future is looking really bright for FRB environment studies. Here's a plot showing the kind of telescope outline. So in white, our telescopes are currently finding and localizing FRBs, and in pink are kind of the newer telescopes, or the ones that are coming online very soon. And you can see here the Meerkat, ASCAP, DSA 110 are responsible for the current FRB host populations. CHIME FRB is the current leader in terms of FRB discovery. But I want to highlight the CHIME FRB outriggers. Sandra's going to give a nice presentation on that tomorrow, I believe. And the CHIME FRB outriggers is basically an upgrade to CHIME to turn it into a very long baseline interferometric array. So we're now in a regime where we have a telescope that can find and localize FRBs to sub-galaxy precision. And then we also have these new upcoming instruments like CHORD and DSA that are going to find tens of FRBs a day and be able to localize them to their galaxy or within their galaxy. So we're in a really exciting time for FRB discovery and localization. And this has been a long journey to get to this point. So this is a plot showing the number of FRB hosts as a function of time, and it's really been a decade of work to get to the 120 hosts that we have so far, which it depends, I guess, what field you're in, whether that sounds like a lot or not. But we have over 4,500 FRBs, so it's a very small fraction of them actually have this host galaxy information. But we're definitely in a regime now where this is going to exponentially grow in the next few years. And I want to just highlight one recent result from the CHIME FRB outrigger team, where we actually localized the first non-repeating FRB to its really sub-galaxy local environment precision. And that's shown here. You can see the localization is this very, very, very tiny red ellipse that you can barely only see in the zoom in. And it's slightly offset from this nearby star forming region in the galaxy. And when we zoomed in with JWST on this region, we found that there's a young stellar population coincident with the FRB position. And so that's completely in line with a young neutron star origin for this non-repeating FRB. And so we're building up our sample, and we're really excited about being able to do a sample comparison of non-repeaters and repeaters to really see if non-repeaters show the same diversity that we see in the repeating FRBs. Okay, so moving on to the radio properties, we see kind of everything when it comes to the radio properties in terms of their frequency structure, time structure, polarization. We kind of see it kind of all over the place. And we don't really have a good explanation for this diversity. Maybe there's distinct progenitors that's contributing here, but there could be other factors. There could be different emission physics at play, or maybe there's propagation effects that are imparted from a complex immediate environment that are introduced in the signal and creating some of this diversity. And so I think it's important that we can start to disentangle this with larger samples to get a cleaner picture and a cleaner understanding of the astrophysics of FRBs. So for progenitors, we already talked about how host galaxies and local environments are really the key there. In terms of the emission processes, so the FRB emission mechanism is split into two camps. You have the nearby models, or the magnetospheric models, where you have some type of mechanism that occurs within the magnetosphere, creates the FRB that we see here on Earth. And then you have on the other side, you have the far away models where you have a central engine that releases energy in the form of a shock, and that shock propagates very far out and interacts with the surrounding medium, releasing the FRB at very far distances. And the main discerning factor between these two classes of models is the predicted emission size. So for the nearby models, we expect that the emission size is going to be very small, coming from within the magnetosphere, whereas for the far away models, we expect that this shock front will light up a much larger region to create a larger emission region. And so one powerful tool to be able to distinguish between these two different emission sizes at extragalactic distances is if we can measure scintillation from a local screen near to the FRB. So you can think of this like stars and planets. We know that stars are twinkling because of scintillation through Earth's atmosphere, and the planets are not. That's because they appear larger on the sky, and so they're no longer point-like with respect to the diffractive scale of Earth's atmosphere. And so you can play a similar game here where the small emission size will be point-like with respect to this plasma screen, and so we see strong scintillation, which is intensity modulation as a function of frequency that you can see here. But as soon as you make this much larger relative to the plasma screen, like the planets, then you significantly reduce your modulation and or you don't see scintillation at all. And so we went hunting for this in CHIME bursts. Like I said, there's like 4,000 FRBs, so lots to go searching in. And we found this FRB, which you can already see in the dynamic spectrum. So this is the dispersion has been corrected here, so there's no dispersion. And you can see there's this intensity variations as a function of frequency. There's these kind of stripes in the dynamic spectrum. This could be scintillation. And so what we did is we took this burst spectrum and we autocorrelated it, which is shown in the orange. And we see two very clear signatures of scintillation in this autocorrelation function. One of them is coming from scintillation from a plasma screen in the Milky Way's interstellar medium, and the other is coming from scintillation from a plasma screen in the host galaxy's interstellar medium. And so this is the first time we've detected scintillation from the host galaxy for an FRB. And so this allows us to ask the question, how large is that emission region for the FRB, given that we can detect scintillation from the host galaxy? And so that's what's plotted here. Again, we have a constraint on the apparent size, right? Like we know stars are bigger than planets, but stars are farther away, and so they appear smaller. So there's this degeneracy between the absolute size of the emission region and the screen distance. And so that's what's shown with this green line here. And overplotted, I have the allowable sizes for the far away models in orange and the nearby models in purple. But what we do know is that we know that this screen has to be coming from within the host galaxy. And so that allows us to place an upper limit on the size of the FRB emission region of 3 × 10⁴ kilometers. And so for this FRB, we know that it's not coming from one of these faraway models. And we've only been able to do this type of analysis one time so far. There are other observational support in the literature around magnetospheric models in a few cases using temporal variability and polarization behavior. But really these studies are kind of in their infancy, I would say. And I do think that there might be even evidence that there are multiple emission processes happening in the literature. So one example I'll show here is these are bursts from a repeating FRB. They show this incredibly complex morphology. They have these sharp structures next to kind of broader, driftier structures. And then similarly over here, I think these are 2 different repeaters actually. And I think that in this Hewitt et al. Paper, we draw the analogy to solar flares, where in solar flares, it's totally different luminosities, timescales, frequencies, but they have these 2 different types of solar flares that can happen at the same time, where you have these kind of sharp structures that are thought to come from magnetic reconnection near the solar surface. And then you have the broader drifty stuff that's thought to come from shocks that propagate out into the corona. And so that sounds very similar to these 2 camps of FRB models, where maybe we have magnetic reconnection happening inside the magnetosphere and shocks plowing out from the central engine into the surrounding environment. And so I think that scintillation is going to be an incredible tool to be able to measure emission sizes across the population and actually test whether they're all coming from magnetospheric processes or maybe there is this diversity across the population. So we can disentangle progenitors with their host galaxies and their local environments, and we can disentangle the emission processes from the emission processes using scintillation. The last thing is their immediate environments. So I mentioned earlier we have these Faraday rotation or the rotation measure, which traces the magnetized plasma. And so for a sample of about 100 FRBs, we were able to study the rotation measures and show that they have rotation measures consistent with Milky Way-like rotation measures, implying that the magnetized plasma in these galaxies is comparable to what we see from the Milky Way. But when you add redshifts, what you can do is you can remove all of that foreground contribution to the dispersion and the rotation measure, and you can constrain the local magnetic field strength. And in this study, what they show is that for a small sample of FRBs, they seem to have a higher magnetic field compared to pulsars. And so then the question becomes, is that because the host galaxies are more magnetized compared to the Milky Way? Or is it because there's a significant contribution coming from the local environment? And I think maybe with some recent study by ASCAP, they actually showed that their rotation measures seem to be correlating with the inclination of the galaxy. So as you go more edge on, you get a higher rotation measure. As you go more face on, you get a lower rotation measure. And so to me, that tells me that the RM seem to be tracing the host's interstellar medium. But I think that here the numbers are quite small. The statistics are not very strong. And so I think there's a lot more work that we can do here, and I'm excited about doing this with the outriggers. But I think it's particularly interesting because one thing we can do is we can probe the interstellar medium of other galaxies. But the second thing is it means that we can find outliers. And I think the outliers can be very interesting for this compact object physics. And we know that there are already some outliers that show extreme and complex circumsource plasma. So here, this is the first repeating FRB, which has the highest rotation measure of anything. It's comparable only to this galactic center magnetar. And so maybe it's in a galactic center-like environment. However, it's off nuclear in a dwarf galaxy. And actually, this repeater is one of the ones that has one of these compact radio sources that I mentioned earlier. And so maybe there's some connection between whatever this compact radio source is and the rotation measure. There's a repeating FRB that shows a magnetic field reversal. So the sign of the rotation measure changes on month timescales, implying the magnetic field completely flips 180. And then on the same source on minute timescales changes its scattering drastically, implying that the local density is changing on minute timescales. And so this is a really complex, turbulent local environment for a source. Now, the final source I want to talk about is this repeater, which showed this kind of steady rotation measure over time, kind of in the few hundred regime, and then out of nowhere jumped up to 2,000 radians per square meter before dropping back down to the baseline. And the interpretation in this paper is that perhaps this source is in a binary system where there's a stellar companion that releases a stellar flare, and just at that time it crosses our line of sight, and we see this magnetized plasma jump in our rotation measurement. We actually discovered this source with CHIME, and so we looked at the rotation measures and we found that they were consistent with what this FAST study we're seeing. But what we found that was interesting was the dispersion measures. So the dispersion measures actually are steadily declining with time, as you can see here. And we think that this is actually consistent with an expanding supernova remnant. So there's some theoretical work to show the dispersion measure versus time predictions for supernova remnant expansion, and our observations fall perfectly in line with that. And then the keen eye in the audience will notice that our one data point near the RM flare also jumps up in DM. And we think that this is consistent with this picture, because as you can see in these nice images here, the density is not smooth, right? There's lots of this filamentary structure, and so it's possible that at this time a filament in the remnant crossed our line of sight and induced a jump in the DM and a jump in the RM at the same time. And so we think it's all consistent within this picture. And yeah, I want to point to Nicole's really nice talk from yesterday, where she is studying this on a population level. So we kind of want to see how unique the source is relative to the broader population, and Nicole's going to be able to answer that. Okay, and this is my final slide. So hopefully I've convinced you that we can use host galaxies and local environments to uncover the progenitors of FRBs. We can use scintillation to uncover the emission physics, and then we can use our radio properties to probe densities and magnetic fields in their local environments. And mostly what I showed today was kind of like individual sources or small samples, but we're really in a regime where we're going to build up bigger samples and actually be able to do this on a population level. Thank you.
Thanks to Kenzie for this beautiful overview of our fast radio bursts on the super fast and exponentially evolving field, basically. I'm pretty sure there's quite a few questions. Is there anything over there? Because I always forget you over there. No? Then up there.
Thank you for the very nice talk. It was illuminating for many aspects. I just wanted to ask if you can explain how do you distinguish the scintillation which is in the host and from that in the Milky Way? It's just because of the frequencies?
Yeah, that's a good question. So we have, like I said in the beginning, we have a map of the electron distribution in the Milky Way from pulsar observations. So we have a prediction of what the scintillation could be from those maps. However, in this case, what you can actually do is because you have two screens, you have two scintillation scales, the same logic applies to the stars and planets example, that they have to be far enough apart to maintain that coherence to actually see the scintillation. And so you know that there's some minimum distance between those screens, which is how we know that one is in the Milky Way and one is in the ISM. And then you can use, actually in this case, we took the most conservative approach in terms of the emission size constraint. So we took the order that maximized the emission size, because we didn't know which one was the host galaxy screen and which one was the Milky Way screen. So we took the most conservative approach. But you could compare to these electron distribution models if you want. Yep.
Thank you.
Thanks for a really nice talk. I'm actually curious a little bit about if you could elaborate what you can get out of the other FRBs that don't have this very strong scintillation measurement. Do you still get some sort of constraint on the emission size, or is it sort of just not there if you don't detect a clear frequency?
Yeah, that's a good question. So if we see scintillation with a weaker modulation, like if we still detect the scintillation, but it's not quite as strong, you can still get a constraint on the size. Yeah, if it's perfectly modulating, then it's an upper limit on the size. If it's partially resolved, then you actually get a constraint on the size. If you don't see scintillation at all, that becomes a lot trickier, because there's other reasons why you could decohere. For example, like if you had a screen that's from some like intervening galaxy along the line of sight, that could decohere your signal. That's irrelevant to the size of the emission size. So non-detections are harder, but I think that there's something we can do on a statistics level once we have a larger population and a larger number of measurements.
Thank you.
So thanks a lot. It was really very, very interesting. I have a question from a totally not expert person. If you can go to the very beginning of your talk. Actually, I have two questions, but one is I think the slide 3, something like that.
Slide 3. How do I go back? Oh. Okay. Oh, this might take a while. Hang on. Oh, and now it's crashing.
Okay, anyway, yes, you really crashed.
Sorry. I've broken the laptop.
So,
Yeah.
yes.
This is very strong scintillation.
So while they are trying to recover in the laptop, I can try to ask my question anyway. You show a plot when you show the magnetars and the pulsars anyway, and the FRBs. And the FRBs, so what I don't understand is that the group of FRBs, do you have some really instrumentation limit or something linked to observation anyway that prevent you, that prevents you to go a bit
like
lower
in here.
luminosity?
Yeah.
Because it seems really you have a straight line lines there. So is it due to instrumentation? Is due to
So this is a somewhat misleading plot because there's other transients on this phase space that I didn't plot. So we know that there's emission in this gap from this magnetar. There's emission that spans about 7 or 8 orders of magnitude from this single source. But actually we don't have, it's not densely populated, this area. And I think it's mostly, I think it's mostly that you can't see like these lower luminosity emission very far, right? There's a jump to get to the nearby galaxies, and then you can't see even like bright pulsar emission at those distances, even though they will exist. And so I think there's just a lower density of emission in here. And then there's also we're building telescopes in the field that are designed to try and find like the brightest things from nearby galaxies. And so that those telescopes are going to be basically designed to probe this parameter space.
Okay, to see if there is a continuum there or something.
Yeah, there is emission here. It's just not very densely populated at the moment. Yeah.
And the second question was about the host galaxies.
Yeah.
So you had a plot where you do the cumulative distributions. I don't want to there you crash it again.
Okay.
Yeah, here.
Yeah.
So yeah, it's not clear to me why you say that they prefer massive galaxies from this plot.
Yeah.
Because I would have said the opposite.
Yeah. So there's the possible is the key word. It was a claim in the DSA study that they prefer mass. There's a lack of low mass galaxies, I think, in this plot.
Okay.
Yeah.
Okay. Yeah, but it's much more difficult to be complete on this low mass side, maybe. Then instead, it's clear that you don't have high mass.
Yeah, exactly. So I think that's why the possible is here. The claim in the literature is that there's a deficit of low mass galaxies. We know that there are some dwarf galaxies. And I think there's some debate about whether the selection effects were properly handled to actually claim that we didn't see dwarf galaxies or low mass galaxies here. So yeah, I totally agree.
Okay, thanks.
Yeah, so also, if I may say something, so the one where you have most deficit of low mass galaxies is actually low redshift. So at redshift 0.2, there shouldn't be a problem to detect a galaxy at that mass. So maybe there is actually something there. So I don't know. That's very interesting. I'm very interested in hosts. So
yeah, no,
we're gonna have a beautiful talk tomorrow by Sandra.
Yeah,
okay.
I would add also that we are in a situation where sometimes we don't see a host galaxy, and those have to be properly accounted for when doing this kind of
FRBs.
sometimes. And so it's possible that those are low mass hosts, and so that needs to be accounted for when doing these kind of studies. Yep.
Okay, so we have to unfortunately stop here. Thanks, Kenzie, again.
Hi, everyone. My name is Alex. I'm a PhD student at the University of Amsterdam. I'm also part of the AstroFlash and CHIME FRB collaborations. And today I'm going to be talking a little bit about how we can trace the origin of FRBs through their local environments using very long baseline interferometry, or VLBI. So as you've seen in the previous talks, we're currently in a bit of a golden age for FRB localization and host identification, from being able to pinpoint the hosts of very far FRBs with redshifts of 2, like Ben mentioned, to sort of amassing these larger catalogs of FRB hosts in general through surveys like Craft and MeerTrap, and now with the CHIME FRB outriggers. So what we've been able to see, for example, is predominantly for non-repeaters, but also just looking at the general FRB population, that FRBs seem to trace the star-forming main sequence of their host galaxies, but this isn't the full picture, and it's important to zoom into specific FRB sources when we can to identify any outliers and get more of the full picture of what FRBs might be. So I'll introduce EVN Precise. This is an ongoing program that I'm part of. It's one of the typical astronomy acronyms, so pinpointing repeating CHIME sources with EVN dishes, but I want to caveat that it's not just CHIME sources. So basically, we take repeating FRBs identified or detected from wide field surveys such as CHIME, follow them up with the European VLBI network, which is a collection of telescopes around Europe, Asia, and South Africa. And basically, the reason we follow up repeating FRBs is because the field of view of the EVN is much smaller. So at least this way we have a preliminary baseband position. But also, the fidelity of VLBI images, or the quality of the images, depends on how much of the UV plane you can sample, essentially. And a lot of the time we utilize the Earth's rotation to get a good image, but FRBs are only a millisecond in duration. So if you're looking at one FRB, for example, this is kind of what you get. You get a sort of characteristic cross fringe pattern where each fringe is sort of dependent on one of the baselines in the EVN and their orientation at that time. So you get to localize the FRB to that sort of point in the middle, but as you can see, there's a lot of side lobe ambiguity. So this precision is like of the order of a few hundreds of milliarc seconds. However, what happens when you have a repeating FRB and you can detect multiple bursts is you can coherently combine them and essentially get a localization that's milliarc second precision. So the size of the beam, and this corresponds to sort of parsec scales at the redshifts of fast radio bursts, allowing you to do multi-wavelength follow-up and really see what's in the local environment. So what this sort of looks like is if you take an initial CHIME baseband localization, which is around an arc minute, you can see there's a lot of different stars and galaxies in the field. You can't really concretely associate it with a host. With the outriggers for further galaxies, you definitely can unambiguously associate the FRB with a host. However, you need VLBI, for example, with the EVN to pinpoint exactly where the FRB is, which if you can see in this image is that tiny red dot on the outskirts of this sort of face-on spiral galaxy. And in the case of the third repeater, FRB 2018-0916A, multi-wavelength follow-up essentially showed that this source, the FRB source, was offset around 250 parsecs from a knot of star formation. And if this were to be a kind of magnetar from a core collapse event, given the ages of magnetars and their kick velocities, this is actually inconsistent with this FRB source being a lone magnetar and more consistent with it being a high mass, a neutron star high mass X-ray binary or a gamma ray binary system. Some other things that EVN Precise has sort of been able to uncover, and this one was touched on by Kenzie, is FRB 2020-0120E was traced to a globular cluster. These are much older stellar populations, so this also isn't consistent with like a core collapse magnetar and more consistent with a dynamical formation channel or another origin for FRBs. And in the case of FRB 2019-0208A, the EVN position actually initially showed that there was no host at the position of the FRB. So that sort of prompted deeper optical imaging, which revealed a low luminosity dwarf galaxy at the position, showing that it is important to get this precision when you can, because some FRBs originate from low luminosity galaxies, and you know sometimes this is the only way to get unambiguous host association, if that makes sense. And another thing that Kenzie touched on is that VLBI has helped us uncover a subpopulation of FRBs with radio counterparts. So these are persistent radio sources, or PRSs, and they're essentially compact, non-thermal, and very luminous sources of persistent radio emission, coincident with a rare few repeating FRBs. We don't know what PRSs are, but so far we have 4 confirmed FRB PRS systems where the PRS has been shown to be like compact and co-located with the FRB. One was the first repeater, FRB 2012-1102A, but now we have 3 more. And I want to focus on FRB 2019-0417A, which is sort of the most recent addition to the field, because with it, we noticed that some sort of interesting common properties were emerging but within this subpopulation. So the first thing is, this is a similar plot to what Ben showed with the Mcgrath relation. What you see here is redshift on the y-axis and extragalactic dispersion measure on the x-axis. In green, you can see a variety of repeating and non-repeating FRBs. And I don't know if it's super obvious, but there is an orange line there. And that sort of represents the extragalactic DM that we'd expect given the Mcgrath relation. So most FRBs tail a bit to the right, and that's because the Mcgrath relation sort of accounts for the IGM contribution, but not necessarily the host contribution of FRBs. So most FRBs do have some host contribution, but FRB PRS systems in red have a much larger host contribution in general. So this means their local environments are much denser than other FRBs, and FRB 2019-0417A actually has the highest local DM of any FRB we've found so far, with a minimum DM of around 1,200 parsecs per centimeters cubed. The other thing is, these systems have very large and variable rotation measures. So the 2 sources that Kenzie pointed out actually both have the one with the highest rotation measure we've ever measured, and the one with the flipping magnetic field or the magnetic field reversal, those are both two FRB PRS systems. So you can see here, this is the distribution of rotation measures or absolute rotation measures from the first CHIME baseband catalog FRBs. And in red, you have the kind of maximum rotation measures of each of the FRB PRS systems. These either tail to the right or are much larger than what we see for other FRBs. And also a lot of them are dynamic. So we see the reversal or we see sort of sweeps in the rotation measure, signifying a dynamic magneto-ionic environment around these systems. And probably one of the most interesting things is even though the sample size is quite small, these systems seem to show an apparent preference for low metallicity star-forming dwarf galaxies. So some work done by Dr. Maria Drau and Dr. Adaisy Ebik at the University of Toronto shows that on the left, we have the R-band magnitude versus redshift. Again, general FRB hosts are in green, whereas FRB PRS systems are the colored stars. You can see that it's predominantly low mass dwarf galaxies. But on the right, looking at the metallicity against the stellar mass of the hosts, you can see that the metallicity of FRB PRS systems is way lower than what we see for other FRB hosts. And in fact, if you overplot the hosts of long gamma ray bursts and superluminous supernovae, the FRB PRS systems have more in common with those than they do with other FRBs. So this kind of implies a potential association with the deaths of massive stars, particularly like rapidly rotating OB stars. The fact that there's a dwarf preference also has certain implications for what these systems might represent. It's been proposed that FRB PRS systems could be like the evolutionary precursor for at least repeating FRBs, where every repeater starts off with like a PRS that fades over time. However, if they all keep coming from dwarf galaxies, that's inconsistent because it doesn't make sense that all repeating FRBs would evolve out of dwarfs into like globular clusters and things like that. So this is starting to rule out FRB PRS systems as evolutionary precursors. And what it implies is that they're either the consequence of their low metallicity environment, so something like a magnetar wind nebula that was spinning so fast, maybe lost angular momentum and then just dumped a bunch of energy, or a distinct FRB engine, maybe a system that includes a black hole, just something different in general. And there's follow-up work at the moment being done by Vic Dong, who's a PhD student at Northwestern University, that is looking into other FRBs with dwarf hosts and seeing if PRSs can be found, including for non-repeaters, to see if we can sort of bridge that question of are non-repeaters and repeaters the same thing. But on the topic of non-repeaters, all of these insights have been for repeating FRBs. Obviously, we haven't been able to gain the same sort of parsec scale local environment insights for non-repeaters. And that's largely because we can't use VLBI in the same way for them. So how can we achieve these insights for non-repeating FRBs in the future? And the answer to that is by utilizing distance. So Kenzie showed RB float, which is basically, it stands for the radio brightest fluence of all time. Very bright FRB detected by CHIME last year. And in fact, it was detected by all three outriggers as well, allowing a VLBI localization. And Sandra will go into the outriggers in a bit more detail tomorrow. But essentially, as Kenzie showed, we were able to get like a 13 parsec scale follow-up of the local environment because this FRB was so nearby, allowing us to see that it's not inconsistent with a compact object formed in situ. And basically, there's future prospects now with the CHIME FRB outriggers. To summarize, what you see here is essentially a proxy for the sensitivity of CHIME versus our angle. And what I mean by that is at 0, it represents the meridian of CHIME. So essentially its field of view. This is obviously where the sensitivity is at its peak, but you'll notice that the sensitivity doesn't drop to 0 when you go out of CHIME's main field of view. And that means that there's some increased sensitivity in the side lobes. Occasionally, we detect an FRB in the side lobe of CHIME. And these FRBs, because the sensitivity is so much lower there, these are 500 times brighter and therefore statistically 20 times more nearby than the general CHIME FRB, meaning that we essentially have multiple RB floats at us disposal if we are able to look into the systematics of the outriggers and localize these with VLBI as well. So in the future with CHIME, we expect to get some precise localization of non-repeating FRBs and start to slowly build up that sample over time. So in conclusion, because of local environment studies, we now know that 1, FRBs require multiple formation channels to explain their progenitors. 2, there's a subclass of repeaters associated with persistent radio sources, and these are sort of emerging as their own thing within FRBs. And 3, the CHIME FRB outriggers will be one of the instruments that will help build up the sample of non-repeating FRBs with local environment studies so we can start comparing repeaters and non-repeaters and hopefully answer some more questions. And that's it. I'll take any questions.
Okay, thank you for the talk. Thanks very much. We have time for one quick question. Over there.
Hi, thanks for the great talk. I was wondering, how do you think we can deal with the non-detections of PRSs in this sort of analysis? I mean, I understand that we can't, you can't be sure of a PRS association possibly without VLBI, but we also do have strong upper limits on any continuum flux. So how can we use those?
So one of the things we can do is there's been proposed to be like a PRS luminosity versus RM relation if these are like, if there's a nebula origin, for example. So there's already a lot of studies doing like follow-up with the VLA because we should still expect to detect candidate PRSs with the VLA and place upper limits on the luminosity of PRSs. So that's something that we can look into. I think if we place deep limits on especially some like nearby FRBs, that could have PRSs, we can start to distinguish what they might be. And also targeted follow-up of FRBs with really high rotation measures or other signatures of like these systems would be interesting as well.
Okay. Thanks to the speaker again. And we move on to the next one. This is here. Did the next speaker make it from the airport? So the next speaker is Jain, and he barely made it. He got his visa on Saturday and made it from Canada. Seems the French embassy is working a bit slowly. So he's going to talk about the modeling of the energy and redshift distribution of FRBs using a second CHIME FRB catalog.
Okay. Hello, everyone. My name is Jain. I'm a first-year PhD student at McGill, working with Professor Victoria Caspi on modeling the intrinsic distributions, intrinsic properties of fast radio bursts, such as what's their energy distribution and what's their redshift distribution. You've heard a lot about fast radio bursts in previous talks. They're highly energetic millisecond duration bursts that show this dispersive sweep such that high frequency signals arrive first in time. And once you correct for the dispersion, you can also sometimes see that there's a frequency dependent scattering. So the pulse is broadened at lower frequencies. These are originating from other galaxies. Their origins are largely unknown. We do have many models to explain what FRBs could be, but there's no definitive consensus on it. And roughly 3% of the FRBs are known to repeat. So that means we have seen more than one burst from any given source. As people have previously talked about dispersion measure, it's a great tool to kind of figure out where the matter in the universe is, because it encodes all the matter an FRB signal is interacting with on its way to us. So that could be from the local environment in the host galaxy, intergalactic medium and intervening galaxy halos, as well as our own galaxy. Yeah, that was a quick overview of dispersion measure. And the big questions about FRBs is really what their progenitors are and how can we explain them. We could look into individual sources, unique sources, such as the ones that are super energetic, like RB float, or the ones for which we have multi-wavelength follow-up. Those are very cool. You could also take another route where you can look at the population of FRB as a broad population, essentially, and try to constrain global properties. So how often do they occur in the universe? How often is there a redshift that their occurrence peaks at? What's their energy distribution, redshift distribution? What is the distribution of DM contributions from their host galaxies? As people before me have talked, that's also something we care about, both to explain FRB progenitors as well as be able to use FRBs as probes. So a lot of these things are interesting because if we, for example, look at how FRB rate density evolves over time, if it correlates well with star formation history of the universe, we can kind of infer that FRBs originate from younger stellar populations versus if it's, not that correlated with star formation history, that would point to older stellar populations. So these are the kind of things we're trying to figure out in this work. And to get a population of FRBs, we go to CHIME FRB. It's a transit telescope with no moving parts. It's situated in Penticton, Canada. It has a 200 square degrees of instantaneous field of view and a wide observing bandwidth, which essentially makes it a great FRB discovery machine. We have recently released a catalog of FRBs detected by CHIME, which contains of more than 3,600 non-repeating FRBs and 83 repeating sources from the first 7 years of its operation. And it's complemented by the injections, which are used to characterize telescope biases. So see Kyle's poster and his flash talk, and also his papers up on archive. And basically what this allows us to do is calibrate for CHIME sensitivity, which is not uniform for all FRBs. For example, if you have we are more sensitive to high fluence events than we are to low fluence, and as well as there's a cutoff at high DMs beyond which we are not that sensitive to FRBs. So CHIME sensitivity to an FRB depends on its properties. So in conjunction, where we have a large data set of FRBs with which is uniformly selected, and we have a system to characterize telescope biases that allows us to do population analysis. We do select for burst such that we have a statistically robust sample. So high detection, high signal to noise, basically to make sure that our sample is not contaminated by bursts that are not quite astrophysical. Events with a DM that's above a certain number to make sure that they're not ambiguously extragalactic, and also a scattering timescale limit, so that because this is the limit beyond which the selection effects for CHIME FRB are not well constrained. I would also like to note that we only use first burst from known repeaters, so that we're not really considering the difference between repeating and apparently non-repeating FRBs. We're only quite just working with FRB sources. And what we do is we consider rate distribution of FRBs as we observe them in fluence and DM. And this distribution can be described as mathematically a function of how many FRBs are produced per unit observed fluence at any given redshift, and at that redshift, how much DM would an FRB be produced at. So this is the physical model, and the model itself is described by fit parameters that control the energetics and the DM components of this observed phase space. And what we essentially do is that we Monte Carlo over the fit parameters to generate synthetic populations of FRBs. We correct for the selection biases, and then we compare with our observed data to infer what are the best fit parameters. So constraining properties that I'll get to in the next slide. Oh, and a quick note that the fluences in the catalog are lower limit for a reason that I will not go into. So we use signal to noise as a proxy for the burst signal strength. So the first thing we look at is what's the volumetric rate density at redshift 0 above some minimum energy and below the scattering cutoff that we have. And we see it's like around 10 to the power 5 from this work, and it agrees pretty well with previous works from different samples. So Shin et al. Used the catalog for the first catalog. This one is at slightly higher frequencies, but the absolute values compare pretty nicely. We can compare the FRB volumetric rate with neutron star magnetar occurrence rates, magnetar giant flares, or type 1 ACE and coarse collapse supernovae, which all seem to be consistent with FRB rates, essentially saying that these can be potential progenitors for FRBs in the local universe. And what stands out is binary mergers. So in the local universe, at least, it seems that binary mergers cannot be dominant source of FRBs. But we don't have to look at just redshift 0. We can see how the rate evolves with redshift. So the orange curve here is our best fit result with the error region in orange as well. And the black line here is the previous result. The green line is showing what the star formation history of the universe is. And the red line is basically just 1. And what you see, what we're trying to do is compare whether or not the FRB rate is tracking with star formation history in any sense. We have reduced our error bars from previous studies quite significantly, but we don't seem to be able to distinguish between FRBs, a population of FRBs that's tracking with star formation versus not at all. Yeah. So we need more data, and as other people have talked about, like host galaxy associations would really help with this. We can also look at the energy function, which we model as a sector function. So essentially, you have a power law, which is exponentially damped after some characteristic energy. And why we care about this is really the maximum cutoff energy, which dictates the energy budget of what FRB progenitors must have. So any proposed progenitors must have the energy budget to accommodate the FRB energetics we see. We also constrained host DM distribution. We model it as a log normal distribution. And the main utility comes from breaking the degeneracy between host halo environments and intervening cosmic web, and would definitely benefit from host localizations as well. And just a summary, I'll leave it here in interest of time. And there's other people who are working on data that would definitely improve the population analysis that we are attempting to do. They're in the audience, and please find them as well.
Thank you, Naman, for this nice overview. We have one question over there.
Yeah, thanks for the nice talk. With respect to Kenzie's comment earlier about the galactic magnetar FRB having a lower luminosity, from your energy distribution, can you comment on whether or not that's a problem at all or just fully expected given the much smaller volume?
Can you repeat the question?
Yeah, right. So, within the Milky Way, you would need something that happens much more frequently to see it versus the very large volume for the FRB. So given your distribution, can you comment if that's just completely consistent or concerning that, the one FRB that we have from a local magnetar is actually less luminous?
I haven't looked at that, but yeah, I'll look at it.
Okay, we can talk offline.
Yeah.
Thanks.
Okay, all right, one more quick question because otherwise you're going to be starving.
Yeah, can you go back to your slides of the energy budget? Yeah, that's the energy budget for one burst or for one source. I mean, you have repeaters.
Yes,
Yeah,
this is
for one burst. Yes, I guess.
Sorry.
Is the energy budget for one burst or one source?
Yeah. Yes, this is we're modeling FRB sources, so we haven't taken repeater information into account.
All right, thank you.
Okay, I'm sorry we have to stop here. Any further questions have to be shifted to the lunch break. And we have 6 flash talks now, of which 5 should be here. One is online. The online one we take in the end. So please all come here in the order that's in the program. And everyone strictly 2 minutes. And I hope you have only one slide. If not, I come and interrupt you.
I can start.
The speaker helper is too slow.
Okay, so hi everyone. Can I go? Yeah. Hi everyone, I'm Andrea Geminardi. I'm in the last year of my PhD in Italy at USP Pavia. My supervisors are Paolo Esposito, Maura Pilia, and Gianni Bernardi, and my thesis focuses on the detection of short timescale radio transients with particular attention to FRBs. And I want to highlight this project where I monitored the fast radio burst repeaters with Italian radio telescopes, as you can see here on the left on the slide. I want to stress that most of the observations were performed with the Northern Cross radio telescope, which is a transit radio telescope that actually is under refurbishment, so it will be upgraded in the next months. We also combined observation with other radio telescopes at different frequencies, and we obtained more than 1,300 observing hours on a total of 21 targets. Our detection threshold is around a few Jansky milliseconds, so we are sensitive to the most energetic bursts from a typical FRBs. On the right, you can see a really bright detection that we obtained on FRB 2024-0114A. And we are about to publish a paper on this campaign, and of course, we will discuss the burst rate of these FRBs at different observing frequencies, and also the energy distribution of the bursts at different frequencies. So if you are curious about this project, please ask me. And if you want, you can also scan the QR code that links you to my poster. So thank you.
Thank you very much. Hi, everyone. My name is Kyle Mcgregor. I'm a master's student at McGill University in Canada. I'm part of the CHIME FRB team, as Naman just presented on before. I operate CHIME's injection pipeline, and this past September, we did a large campaign of about 500,000 injections across or covering the FRB parameter space, with which we can measure whether each injection is detected or non-detected. This gives us a binary data set for which we can construct a statistical model for how well CHIME is at detecting different types of fast radio bursts. One of the things that we're most curious about is the scattering distribution. Scattering is a temporal effect and it's frequency dependent. And there's a very strong selection bias against highly scattered fast radio bursts. And we can use this statistical model, as I present in my poster and paper that's up on the archive, to debias the observed distributions of FRBs, including notably the scattering distribution, of which there's a large population of highly scattered FRBs, which we infer, and we try to constrain the tail behavior of it at high values. And we compare this to another FRB survey, which is at higher frequency, that should be better at detecting highly scattered FRBs. And we find that it agrees with an interpretation of it being a flat or slightly downturning distribution at high values. Thank you.
Hi, everyone. My name is Natalie Lebaron. I'm a PhD student at University of California, Berkeley, working with Rafaela Margutti and Ryan Shornock. Hopefully my poster will come up here in a second.
Sorry. I think now for the time. Ben, how do you put this? Okay, yeah.
Anyway, I'm presenting a poster on one of these luminous fast blue optical transients, which are very interesting, recently defined class of transients, noted for their very luminous emission, as well as their fast time scales, rise fade under 10 days, blue colors, and also detected X-ray and or radio emission, as you'll hear more after lunch. I think it's fine if it's just.
It's the second one, no?
The bottom one.
The bottom. Oh. I'm sorry. Yeah, sorry.
Should be good. Thank you. Yeah, so again, I'm presenting on AT 2024 WPP, which was a very extreme example of one of these luminous fast blue optical transients, reaching an excess of 10 to the 45 ergs per second at peak, making it the most luminous known fast blue optical transient. This transient, its luminosity enabled fantastic data set all across the electromagnetic spectrum, including the third optical spectral sequence of an LF bot, which showed very similar evolution compared to other LF bots, being very featureless blue at basically all times, and then at later times showing features of hydrogen and helium in its spectra. That said, these features were very interesting within these three examples, showing these two distinct velocity components, which is very unprecedented in basically any astronomical transient. So you see two distinct velocity components, one blue shifted at about 6,500 kilometers per second, and another one much closer to rest. We also found the second LF bot near-infrared excess observed for these transients, second compared to the other one, which has near-infrared sampling, which is the prototypical 18 cow. So this defines these near-infrared excesses as a characteristic feature of this transient class. And we interpret these near-infrared excesses either as consequence of dust reprocessing or as a consequence of a free opacity effects in a extended scattering medium. In any case, My poster is outside, and I am very happy to talk more about these interesting transients. Thank you.
Hi everyone, I'm Zoe. I'm a PhD student in Liverpool John Moores University, and I'm going to be talking to you today about our latest two LF bots, AT2026 DBL and AT2026 NIK. As Natalie very kindly just introduced, LF bots are this new and mysterious transient that we think have a common origin, but we're not exactly sure what this origin is. So DBL and NIK are only our 14th and 15th respective LF bots that we've discovered so far, so our sample size is still pretty low. Photometrically, we see DBL has a very, very similar light curve to 2024 WPP, but specifically also to our prototype event, 2018 COW. So it has this steep power law decline. It peaks at around minus 21.3 in the G band. And yeah, it pretty much it maps 2018 COW's light curve very well. However, NIK kind of has a different shape to its light curve, so it's a little bit unique. It's a little bit similar to events such as 2024 AHP at earlier times, but at late times it seems to be doing its own thing. So this kind of unusual light curve, coupled with the fact that we have not detected it in the radio yet, and it has fainter than we would expect early time X-ray luminosity, might represent a bit of an outlier in the LF bot class. There are ongoing observations, so we will see just how much of an outlier it is in due time. Spectroscopically then, both LF bots just show a featureless blue continuum right up until late times, so we can rule out any emission lines as strong as 2018 COW, but because we only have spectra up until 28 days, we can't rule out any later time emergent features like we saw with 2024 WPP. So if you'd like to come see my poster, it's outside until tomorrow, and I'm here until Thursday, so come talk to me whenever. Thanks very much. Yes.
Okay, yeah, hi everyone. Myself is Shiho from Liverpool. And this one was done with my PhD student, Tom Baxter and Will Stone. And we revisit a bit to exotic system. It's a double TDE, where basically binary star system approaching to supermassive black hole and binary members are tidally disrupted. So why we care like this? And this one basically motivated by recent very extreme event, very bright, and a long time scale TD event. Interpretation is a bit still in debate, but one possible scenario is, let's say, 15 solar mass stars tidally disrupted by supermassive black hole. And in that case, that kind of event rate is extremely low compared to solar mass scale TD event. Magnitude can be, intrinsic rate can be several order magnitude smaller. And even take into account the brighter luminosity, maybe observation rate, still maybe fourth order magnitude smaller compared to standard, let's say, TD event, right? So question can be, WTD can mimic such massive star TDE. Advantage, let's say, if we consider smaller mass components, more abundant, and lifetime is longer, and still smaller, but still, let's say, massive stars can be in binary form or multiples. And this, let's say, here, schematic diagram showing left panel is, let's say, single star, and the right side is, let's say, binary disruption. And binary, once approached to massive black hole, initially tidally separated. And let's say here's mechanism, one star is put in hyperbolic orbit and the other in elliptic orbit. In that sense, once actually each component tidally disrupted, mass distribution in energy space for each debris is offset. And it can cause fallback time difference, but if fallback time difference is small enough, that kind can event mimic single tidal disruption event. So we discussed encounter efficiency using Monte Carlo simulation. Okay, both stars must be tidally disrupted, and binary need to survive perturbation by other stars can approach to massive black hole, or if you consider 10 to 8 solar mass, that kind of thing. Tidal radius very close to event horizon scale, and where relativistic effect important, including direct capture. That kind of thing we need to care. And at the end, we discuss also the possible delayed radial flares, where when you calculate, it's in deep Newtonian regime, and self-absorption effect can be very important. And I don't discuss that much time to discuss detail, but if you're interested in any aspect, I'm very happy to chat with you during lunchtime or anytime. Yeah, thank you very much.
Okay.
And the last one is online.
Can you hear me all right?
Very good.
Okay, perfect. Hi, everyone. So I'm Anja, first year PhD student at the University of Amsterdam. And I'm working on developing a machine learning model that is able to model the superstructure of astronomical transients. So as you all know, transients encode a lot of information about their progenitors or emission mechanisms within their signatures. And so by modeling the time variability within the signals of these transients, we can gain a lot of information. So the model we have developed is able to fit a lot of transients. It's very flexible, so it's able to fit a lot of astronomical transients. And it's able to do that very quickly. So we can fit multiple transients within seconds, which is very important also given the rise of a lot of new data that needs to be analyzed. And so for now, we have applied our model to fast radio bursts. So on the left here, you can see an example of a FRB light curve. And FRB can be modeled as a superposition of individual subbursts. And for each of the subbursts, we use a skew Gaussian to model them. So one of the difficulties then is the unknown amount of subbursts within a light curve. But our pipeline tackles this in pretty much inferring a probability of a most likely amount of subbursts within each time series. And then for each of the components, as you can see on the right for an example simulated FRB and a CHIME FRB, it gives a fit, and then it gives posteriors for all of the model parameters. So for your peak times or skewnesses that then describe your burst. So as I already said, it's pretty, although I've only applied it to FRBs, it's pretty flexible. So as long as you have a way of generating simulations for another transient, you can apply to any other transients. And yeah, if you're further interested in reading about this, feel free to check out the poster. And if you have any other questions or any other transients you would want to apply this to, feel free to reach out to me. Thank you for listening.
Okay, thank you to all the speakers of the morning session. Is there any announcement?